Question 13, Part B. Particle A is projected from the origin with initial speed v meters per second at an angle theta with the horizontal plane. At the same time, particle B is projected horizontally with initial speed u meters per second from a point that is capital H meters above the origin as shown in the diagram. The position vector of particle A, t seconds after it is projected, is given by Ra of t equals Vt cos theta for the horizontal component and Vt sin theta minus half gt squared for the vertical component. Do not prove this. The position vector of particle B, t seconds after it is projected, is given by Rb of t equals ut for the horizontal component and capital H minus half gt squared for the vertical component. Do not prove this. The angle theta is chosen so that tan theta equals 2. The two particles collide. Part 1. By first showing that cos theta equals 1 over the square root of 5, verify that v equals the square root of 5 times u. It is given that tan theta equals 2, which equals 2 over 1, where theta is an angle in quadrant 1. In other words, it's acute. I've sketched a right angle triangle to model this situation. Here is the opposite side 2, here is the adjacent side 1, here's angle theta, and h represents the hypotenuse. So to find the length of the hypotenuse, we use Pythagoras' theorem. So h is equal to the square root of 1 squared plus 2 squared, and 1 squared plus 2 squared is 5. So h is equal to the square root of 5. Hence, cos theta is equal to adjacent over hypotenuse, so that's 1 over the square root of 5. Now the particles collide when their x-coordinates are identical at the same time. In other words, Vt cos theta is equal to ut. So we're equating the horizontal components of Ra and Rb. Now we're going to divide both sides of this equation by t, assuming t is greater than 0, of course. So we get v cos theta is equal to u. And we've previously shown that cos theta is equal to 1 over the square root of 5. So v divided by the square root of 5, which is identical to multiplying by 1 over the square root of 5, is equal to u. And then rearranging this equation to make v the subject, and we do that by multiplying both sides of the equation by the square root of 5, we get v is equal to the square root of 5 times u as required. Part 2. Show that the particles collide at time capital T equals capital H over 2u. When the particles collide, their y-coordinates are identical at time capital T. So equating the vertical components of the two particles at time t equals capital T, we get v times capital T times sine theta minus half g times capital T squared is equal to capital H minus half g times capital T squared. Now we can cancel the negative half g capital T squared from both sides of the equation. So we get v times capital T times sine theta is equal to capital H. Now, given that cos theta is equal to 1 over the square root of 5, we can deduce that sine theta is equal to 2 over the square root of 5 if we refer back to the right angle triangle from part 1. So that's the opposite side over the hypotenuse of the square root of 5. And we're given that v is equal to the square root of 5 times u, which we also found in part 1. Hence, v times capital T times sine theta is equal to the square root of 5 times u times capital T. So we replace the v with the square root of 5 times u, and sine theta is equal to 2 over the square root of 5. So square root of 5 times u times capital T times 2 over the square root of 5 is equal to capital H. Now the square root of 5 here will cancel with the square root of 5 here. So on the left hand side, we're left with 2 times u times capital T is equal to capital H. Dividing both sides of the equation by 2u, we get capital T is equal to capital H over 2u as required. When the particles collide, their velocity vectors are perpendicular. Part 3. Show that capital H equals 2u squared over g. The velocity vectors of both particles, VA and VB, are found by differentiating their position vectors with respect to t. So VA of t is equal to V cos theta for the horizontal component and V sin theta minus gt for the vertical component for particle A. And VB of t is equal to u for the horizontal component and negative gt for the vertical component for particle B. Now at time t equals capital T, VA is perpendicular to VB. Hence, the dot product of VA and VB is equal to 0. So in other words, V cos theta for the horizontal component, V sin theta minus GT for the vertical component of particle A, dot product with U for the horizontal component and negative GT for the vertical component of particle B equals 0. So performing the dot product by multiplying the horizontal components and the vertical components separately on the left-hand side, we get uv cos theta minus g times capital T outside of v sin theta minus g times capital T in brackets equals 0. Now, we can express V in terms of u. We found cos theta in part 1. We also know what sin theta is as well, which we found in part 2. So we have u times the square root of 5 times u times 1 over the square root of 5 minus g times capital T times the square root of 5 times u times 2 over the square root of 5 minus g times capital T in brackets equals 0. So expanding the brackets, collecting like terms and simplifying where necessary, we get u squared minus 2 times u times g times capital T plus g squared times capital T squared equals 0. And the equation can be rewritten as u squared minus 2u times g times capital T plus g times capital T in brackets all squared is equal to 0. Now we have a perfect square on the left-hand side. So u minus g times capital T in brackets squared is equal to 0. Hence u is equal to g times capital T. Now we found capital T from part 2. Capital T is equal to capital H over 2u. So u is equal to g times capital H over 2u. And multiplying both sides of the equation by 2u, we get 2u squared is equal to g times capital H. And then dividing both sides of the equation by g to make capital H the subject, we get capital H is equal to 2u squared over g as required. Part 4. Prior to the collision, the trajectory of particle A was a parabola. Do not prove this. Find the height of the vertex of that parabola above the horizontal plane. Give your answer in terms of capital H. The first thing we need to find is the time taken for particle A to reach the maximum height, and that occurs when the vertical velocity of particle A equals 0. In other words, v sine theta minus gt equals 0. And we need to solve this equation for t. Now, v sine theta is equal to 2u from before. So we get 2u is equal to gt. Dividing both sides of this equation by g, we get time to maximum height is equal to 2u over g. Now, the height of particle A at time t equals 2u over g is found by using the vertical component of the position vector for particle A. That is, ya equals vt sine theta minus half gt squared. So substituting 2u over g for t here and here, noting again that v sine theta is equal to 2u, we get 2u times 2u over g minus half times g times 4u squared over g squared. And that equals 4u squared over g minus 2u squared over g, which simplifies to 2u squared over g, which equals capital H from part 3. Therefore, the maximum height of particle A is capital H meters at time 2u over g seconds.